Hi, everyone. Today we are going to introduce the idea of energy. So, this is going to be probably one of the most important units of this entire school year because College Board really likes to focus on energy, laws of conservation of energy, and really how energy ties into everything else that we've learned so far this year. So, energy also is a really good review of the material we've learned because we're going to do a little bit with kinematics, a little bit with forces, which was mechanics. And so you'll really see that in our energy unit. In this unit, we will cover both energy and then also momentum. Okay. So, what is energy? What are some things that you know about energy? Okay. Um, what are some facts that you know? What's something that you know about energy? Go ahead and answer that for me. So, energy is the property of a system that measures the capacity of doing work. Or, in the most basic definition, energy is the ability to do work or the ability to cause a physical change. So, if I transfer energy from one spot to another, I am giving an object maybe the ability to move or to do work on something. So if you drink a Red Bull or a Rockstar or a Monster, you are absorbing a chemical energy, a chemical potential energy, and that's going to give you more energy or caffeine or something like that. If you kick a soccer ball, you're giving that soccer ball energy, and giving that soccer ball energy, you're giving that ball the ability to move through the air. Okay. Now, work is the transfer of energy. So when you kick that soccer ball, you are doing work on the soccer ball to transfer that energy. So you are applying a force to cause that ball to go a certain distance. So when we look at the different types of energy, and this is going to basically sum up everything that we're going to look at, we can look at kinetic energy, which is the energy of motion. Kinetic energy, the symbol is K or Ke. And the equation for kinetic energy is 1/2 mv squared. Then we have elastic potential energy, our elastic potential energy or our spring potential energy. That's going to be the energy that's stored within, say, for example, like your suspension on your car. You've got these springs, and that's going to be the spring force is going to be really tight on that spring. So there's a lot of stored energy in that. Okay, so spring potential energy is 1/2 kx squared, and we will go over that a little bit later. Gravitational potential energy, if you hold up your pen right now, and you drop your pen on the desk that you're sitting at. That is an example of gravitational potential energy converting into kinetic energy. So holding the pen up in the air, the pen has stored potential energy. Or even think about like a bouncy ball. Bouncy balls are my favorite example to use just because, it makes you revert back to being a small child and playing with a bouncy ball. But when you drop that ball, you're converting potential energy to a kinetic energy. And then down at the very bottom, the ground, that kinetic energy is going to go into the elastic potential energy that's stored, and it's going to hit the ground. And so the combination of the elastic potential energy and the kinetic energy of hitting the ground, you're going to end up having sound and maybe a heat transfer. There are all of these different systems or different parts at play in the system that we're observing. So our mechanical energy, what is our mechanical energy? Our mechanical energy is the total energy of the system. So right here we have M, the mechanical energy, or ME equals E total, or the total energy. And then you also have thermal energy. And thermal energy is actually something that you studied a lot of in your chemistry class when you talked about maybe the thermal energy going into changing the phase of something or changing the temperature of something. There was phase energy and then there's thermal energy. So thermal energy is going to be your heat, like think Q equals MC delta T, something like that. So let's go back to work and what is work? Well, work, remember, we had said it's the transfer of energy and is done when a force acts on an object. So when I apply a force, to cause an object to move a certain distance, then I am applying work on it. But what's really important is that work and the force need to be, the force and the distance need to be in the same exact direction. So, for example, if I have a box, and this was the example given in the video that you just watched, and I am applying a force on that box. The force that is doing the work is just this force right here if I'm moving a certain distance. So I'm moving a certain distance, so I really only want to look at that force. And that's where we end up getting the FD cosine theta, because if that's our theta, we're really looking at the cosine theta there. So W is work, and that's the transfer of energy into or out of an object by mechanical means. Theta is the angle between force and distance. But really, we don't end up using the cosine theta if our force and our distance are already in the same direction. Now, the units for work are joules, because joules is a Newton times a meter, which is the same as kilograms times meters squared per second squared. And that comes from force equals mass times acceleration. So we've got an acceleration times the distance times another mass. Okay. Now, work and energy are scalar, but the positives and the negatives are really going to affect your results. And I really like a video that's posted on the Flipping Physics website if you're having a hard time with this. And he talks about positive and negative work. Okay. So positive work is when energy is transferred into an object, and negative work is when energy is transferred out of an object. So, like, for example, when someone's like pushing against you, it's like taking all the wind out of your sails. Okay. Like, it's like when you have negative work or work done against you, it like takes energy out of you. But work on you, someone's pushing you, then that's going to give you energy, right? And zero work is possible. Zero work is possible when our force and our distance are going to be perpendicular to each other, or at a 90-degree angle. So can work be zero? And we just answered that. So when you're looking at a situation right here, if the force right here with this man holding his briefcase, he is lifting up a suitcase or a briefcase, but he is not applying the force on that suitcase in the same direction as the distance that he's traveling. And so therefore there is no work being done. Now, when he lifts the suitcase up, in this case, so lifting it up from ground level, lifting it up, then there is going to end up being a work done. But in this case, if he's just sitting there holding the suitcase or the briefcase, then there is no work. If distance equals zero, there's no work. And if your force and distance are 90-degree angle, then you would end up having no work. So let's look at an example together, okay? So we have a 3-kilogram block is sliding across a frictionless surface when a 20 Newton force is applied and it begins to act as shown in the diagram. If the force acts as the block moves 3 meters to the right, calculate the work done by the applied force. So if we think about it, our distance is going to be 3 meters this way. That's what our distance is. Okay. So if you look at that, then the force that we're going to be concerned with is going to be this force right here. Okay. Now, in this case, you're not going to be looking at your cosine, and that's why it's really important to understand what does that cosine theta mean? Okay. So I'm going to look at this problem in 2 different ways. One way that I can look at it is work is equal to the parallel force to my distance. Okay. And the parallel force to my distance is going to end up being, it's going to end up being 20 newtons, but it's going to be in the negative direction. So negative 20 newtons sine 35, okay, times the distance, which is going to be 3 meters, okay? That's going to be meters, and this is going to end up being newtons. And then you're going to end up getting joules, and you're going to get negative 34.4 joules. Okay. And so that tells you the direction that the work is being applied. Now, here's the deal. If you're sitting there and going, but Ms. Palachuk, you said that your work is FD cosine theta. Okay, fine. So let's take a look at that. Work equals FD cosine theta. But in that case, the angle that you're dealing with is really this angle right here. That's the angle that we're looking at. Okay. And so we're going to be looking at F is our 20 Newton force. Okay. And then 3 meters is our distance. And then our cosine 125 degrees. And it's 125 degrees because it's 90 plus 35. And that is also going to give me negative 34.4 joules. Now, you may look at this and you may say the way I did it the first time makes more sense to you. That makes more sense to me. But you might look at it and go, nope, I need to know that it's FD cosine theta. If that is you, the challenge that you're going to run into is that when we're just trying to memorize equations and we don't understand the equations, then we're not going to be able to have great results in every single type of problem. If we really understand the equation and understand what work really is, then you're going to have better luck. Okay, so let's look at another problem. This other problem says a 20 kilogram block slides down a 30-degree incline at a constant velocity. Calculate the following as the block slides through a distance of 2.1 meters down the incline. So as much as you really thought that you were completely finished with forces, forces are not ever going to go away. So we're looking at this ramp, and it's a 30-degree ramp. And we have a box, okay? And it says that it's moving at constant velocity. Because it's moving at constant velocity, there actually has got to be a frictional force working against it to cause it go at constant velocity. So we have a frictional force. We have our normal force. Okay, and then we have our force due to gravity. Okay, and then the distance that it's going to be traveling is going to be this way. 2.1 meters is our distance. Okay, and it says figure out the work done by gravity. So we want to figure out the force of gravity that is in the direction of the motion. So we are looking at just this piece of gravity, that y piece, or the x piece of gravity. So the work done by gravity is equal to force of gravity in the x d. Okay, and really our force of gravity in the x direction is going to end up being 20. So it's going to be mg sine 30. And then times 2.1. Okay, so this is my force of gravity, and my x is mg sine 30. Okay, and so that's going to end up giving me that the work done by gravity is 205.8 joules. Okay. Then the work done by the normal force. Well, you got to think about this. Your normal force is going this way, and it's perpendicular to the ramp. And since it's perpendicular to the ramp, cosine 90 is going to be 0. So the work done by the normal force is equal to 0 because your force and your distance are perpendicular to each other. Okay. Now the work done by friction. Well, what is our force of friction? Our force of friction in this case is equal to our weight in our x direction, okay? And when we say weight in our x direction, it actually might even be better for me to change that weight, the W, to a force of gravity, because we have W for work, force of gravity in our extraction. And the reason for that is because it's moving at constant velocity. So the work done by friction is going to be 20 times 9.8 times sine 30. But remember, it's going to be in the negative direction. Okay, it's going to be in the negative direction. And that's because frictional force and our force of gravity in the x direction are opposite each other. And then times d. Our d is going to end up being 2.1 meters. Okay, and that's going to end up giving me negative 205.8. So what's the net work done on the box or the block? So work net is the sum of all of the works, okay? And so that is going to be equal to the work due to gravity plus the work from friction plus the work normal. Work due to gravity is 205.8, okay? And then work done by friction is negative 205.8 plus 0. And that's going to end up giving you 0 joules. And I need you to ask yourself, does that make sense? Does that make sense? And so how do we make that make sense in our brain? Well, if we're looking at the net work, that means we're looking at the net force times the distance, okay? Well, net force, what is the net force in this situation? Well, we know that acceleration equals 0 because it's a constant velocity. And therefore, that's what those little dots mean, F net equals 0. So your net work equals 0 if you have a constant velocity in this case. So now, how do we use graphs? We have used graphs for everything so far this year, and this unit is not going to disappoint here. So it is really important for you to understand why we would use a graph when it comes to work. And the reason we would use a graph is, in this case, I have force on my Y and position on my M. And remember, if you go back to our very first unit, I said that if you can multiply Y times your X value, okay, to give you some kind of value that we know in physics, then that means that the area under the curve gives you that value. Okay. Now in if you watched the Physics Girl video, in that video, which is really, really good, or it would be not in the Physics Girl video, but in the crash course video, one thing that she talks about is she talks about the integral. And so yes, if you are in calculus or you've already done calculus, then you know the area under the curve is going to be the integral. But in this case, I could figure out what the work done in this system is, because I would do my work is equal to my force times distance. So my work is the area under a force versus position graph. Okay, so if I look at that, I have my area here, okay? My area there is going to be 40 newtons times 2 meters. That's going to be 80 joules. And then here, I'm going to have negative 20, and then I'm going to have 2, and it looks like I'm going all the way to 7, so times 5. Okay, and that's going to give me negative 100 joules. So my net work, in this case, my net work is equal to 80 minus 100. So I end up getting negative 20 joules. Okay, So my net work in this case, and why would I use this? Well, notice my force is varying. So if my force is varying, this is a perfect tool to use, and you will definitely see graphs on your AP Physics test. So let's look at a sample problem. The given graph shows the force versus distance compressed for a pillow exerting a force on an egg in bringing it to a stop. Use the graph to calculate the work done by the pillow during the entire 15 centimeters. Okay, so we need to figure out what our work is, and we want to split this graph into two or into three different sections. So we're going to go like this, okay? And so in this case, we're going to use 1/2 base times height. So 1/2 base, our base is 0.03 meters times our height, which is going to be 30 newtons. Okay. Right here, I'm going to have my base is 15 minus 3, so I'm going to have 0.12 meters times my 30 newtons. And then right here, I'm going to have 1/2 my base, which is 0.12 meters, times, it looks like it's about 10 newtons. And when I end up adding all of that together, I get 0.45 plus 0.6 plus 3.6. And when I do that, I end up getting a value of 4.65 joules. So please do not ever forget that the graphs can always tell us something. The work, the net work, is equal to the area under an F versus, we can say D for distance graph or X for displacement graph. So mechanical energy, we've already kind of talked about mechanical energy, but when we're talking about mechanical energy is the energy that an object has due to motion or position, okay? And we already said that our mechanical energy is equal to the total energy of a system, okay? So our mechanical energy can be broken down into two different categories. We have our potential energy, and that's the energy of non-motion, something that's stored, the potential to do work, okay, or the potential to have energy. So we have gravitational potential energy, and we're also going to talk about another type of potential energy, which is spring potential energy. Now, potential energy can be designated as PE, or through College Board, you'll see a U for potential energy. So here I'm writing spring potential energy is 1/2 kx squared. And again, you'll see that in a little bit, but I just want to make sure that we point that out. And then kinetic energy is 1/2 mv squared. So these are going to be three very important equations here, okay? So remember, GPE can be rewritten as UG for gravitational potential energy equals mgh, okay? Energy is neither created nor destroyed, but it can be transferred from one form to another. And here's the thing, scientists have used this transfer of energy forever. I mean, just look up a Rube Goldberg device, okay? Think about something like that. Or if you've ever played the game Mousetrap, when you played that game as a kid, Mousetrap had a pretty cool little Rube Goldberg device going on there on that board game. So energy is neither created nor destroyed, but it can be transferred from one form to another. Okay, and so it is a conserved quantity, and that was something that we looked at in our last video. It is very important for you to understand that sometimes that energy can be transferred into something like heat or light or something like that. Okay. So another thing I want to look at with this is when we're looking at our energy, what types of energy do we have? So our mechanical energy can be split into two different categories. We have our potential energy and our kinetic energy. Examples of potential energy would be gravitational potential energy, so UG, elastic potential energy, which would be US for our spring, or chemical potential energy, which we do not cover in this class, but that would be UCH. Then kinetic energy is going to end up being thermal energy, sound energy, electrical energy. But the most important thing for you to remember about kinetic energy is that it's 1/2 mv squared. Okay, and it's the energy of motion. So this is such an important slide. I want you to take a moment to really take it all in. When we look at work equals force times distance, force equals mass times acceleration, and v squared equals v initial squared plus 2ad or 2ax, can you write an equation for work in terms of mass and velocity? Can you do that? Well, let's see. We have work is equal to, I'm going to use substitution here for my force. So I'm going to use mass times acceleration times our distance. Okay. Well, hold on a second. Right here, I have acceleration times distance. So can I rearrange that equation? Well, I can. V squared minus V initial squared equals 2AD. Okay, so we have A times D, or A times displacement, is equal to 1/2 times V squared minus V initial squared. So let's go ahead and substitute that in down here. So we end up getting that work, okay, I'll bring that down here. Work is equal to mass times 1/2 times V squared minus V initial squared, okay? So let's rearrange that even more. Work, or net work, is equal to 1/2 mass V squared, V final squared, minus 1/2 mass V initial squared. Okay, so what's 1/2 mv squared? Well, that's kinetic energy. So this is kinetic energy final minus kinetic energy initial, or I or O is fine. So how can we rearrange that even further? The net work is equal to change in kinetic energy. Okay, and that triangle, just so we are all clear at this point, that means change in. Okay, so net work is equal to change in kinetic energy. And that is one of the most important things that you will learn in this unit. This is called the work energy theorem, and we just proved the work energy theorem. Net work is equal to the change in kinetic energy. Okay, so let's take a look at another practice problem. When we look at this problem, it says a 6 kilogram block is initially sliding at 5 meters per second and is later moving at 8 meters per second. So I'm going to underline my most important stuff. Calculate the initial kinetic energy. So I'm calculating the kinetic energy initial. So kinetic energy initial, or I, is equal to 1/2 mv initial squared, 1/2 mv squared. So I'm going to take my 1/2 and I'm going to look at my equation, or my problem. 1/2, my mass is 6 kilograms, and my initial velocity, initially sliding at 5 meters per second squared. So I have 1/2 times 6 times 5 squared is going to end up giving me a value of 75 joules. Calculate the work done on the block to cause its increase in speed. Well, we know that net work is equal to change in kinetic energy based on what we just derived. Okay, so I need to figure out what my final kinetic energy is. Well, my final kinetic energy final equals 1/2 mv final squared. And that's 1/2 times 6 times 8 meters per second that's what's given to me in the problem right here, squared. Okay, and that's going to end up giving me a value of 192 joules. So my change in kinetic energy is going to be my kinetic energy final minus my kinetic energy initial. 192 joules minus 75 joules ends up giving me a value of 117 joules. So the work that's done on the block that causes the increase in speed is 117 joules. And that makes sense. It's a positive number because it's increasing in speed. It's going from slower to faster. How do you do that? You have to add energy to that, okay? Now, the next question says a 1,200 kilogram car is traveling at 18 meters per second when it applies the brakes. So applying the brakes, there is a force being applied there. If the brakes allow friction to exert a 2,000 Newton force on the car, and the brakes are applied for 50 meters, how fast is the car moving when the brakes are released? So we're looking at how fast is when the brakes release. So we're looking for V final. That's what our question is. Well, we know that we have a force is 2,000 newtons, okay? And we know that the distance is 50 meters. But remember, our force that's being applied is negative 2,000 newtons because it's being applied against the car to slow it down. We also know that the car has a mass of 1,200 kilograms, and we know that our V initial is 18 meters per second. So when you look at a problem like this, you might think, I don't know where to even start, okay? Well, when you have a force being applied at a certain distance, a force being applied over a certain distance, there is work being done in that system. So our work is equal to force times distance. Well, we also know that our net work is also equal to our change in kinetic energy, okay, which is 1/2 mv and v final squared minus 1/2 mv initial squared. So we end up having that our force times our distance, our force is going to be negative 2,000. So negative 2,000 newtons times 50 meters is equal to 1/2. I'm going to bring my m out, my 1/2 m out. So 1/2 times 1,200 kilograms V final squared minus V initial squared, which is 18 meters per second. Okay, so I end up getting this, ends up giving me 600 kilograms. So I'm going to divide both sides by 600 kilograms. And then I'm going to add 18 meters per second squared to both sides, okay? And then that's going to end up giving me my V final squared, okay? And then I'm going to square root that. So when I plug that into my calculator, and don't forget to make that this value has to be negative. So negative, and then I'm going to add 18 meters per second. Okay, and then I'm going to square root that. I'm going to end up getting V final is equal to 13.6 meters per second. Okay. So when we look at our gravitational potential energy, or our different types of potential energy, gravitational potential energy is mgh, mass times gravity times height. So it's going to be dependent on how high something is lifted from a certain distance. Now, it's all based on your reference frame. So you set the zero value, okay? Remember that mass is in kilograms, and in a lot of cases, we're going to use, or you can use, G equals 10 meters per second squared, or 9.8 meters per second squared. Okay, so GPE, or gravitational potential energy, is maximum at the highest point. This is your highest point on your roller coaster. Highest point is going to be your total energy. That's your maximum energy. If an object is not moving at the highest point, the gravitational potential energy is equal to the total mechanical energy. Then we also have our spring potential energy. Our spring potential energy is our stored energy in our spring. Our spring potential energy is 1/2 kx squared, where k is your spring constant, is how stiff your spring is. So you've got some things, like say you had a dart gun or something. Your dart gun, your spring might be pretty loose, or like think about like a Nerf gun, okay? Your spring in there is pretty loose compared to the springs in your car, the spring system in your car, because your car is more reliant on those springs so that you're not going ba-bong, ba-bong, and like bouncing up and down in your car all the time, right? So this is your spring, your stiffness constant. And that's measured in newtons per meter. And then x squared is going to be your distance, or the distance stretched or compressed. So let's look at our very last question for today. And our last question for today is a potential energy question. It says a 30 kilogram mass is hung from a spring with a constant of 200 newtons per meter, which has the effect of stretching the spring down a distance of 1.47 meters. Calculate the increase in elastic potential energy of the spring. So our increase, or our change in our spring potential energy, so spring potential energy is equal to 1/2 kx squared. So we have 1/2 times our spring constant, okay, times 1.47 meters squared. And that's going to end up giving me 216.1 joules. Now it says calculate the decrease in gravitational potential energy of the mass. So if we look at that, this is our mass and it's being hung by a spring. So this is our initial position. And now all of a sudden, our spring stretches and we've now gone to this height. Okay. And so when we're looking at this, this is our change in height. Okay. Well, our change in height is negative 1.47 meters. So our gravitational potential energy is equal to mg change in h. Well, our mg change in h is 30 times 9.8 times negative 1.47 meters. And that ends up giving me a value of negative 432.18 joules. Okay. So hopefully these notes were helpful for you in just helping you get a head start, or get started on your assignments for this, for today's lesson. If you have any questions, if you need help, please go ahead and let me know, and I will gladly help you out.